Now, damping. If you're damping, then obviously your equation of motion looks like this, okay? It's the same thing we had before, except this time we've got a Cx dot term in here, which gives us our damping. And the same approach gives us that, okay? So if we substitute in this term and then pre-multiply by this term, we get this term, okay? And we know that if we got phi correct, this term is a diagonal matrix with 1s down the middle. This term is a diagonal matrix with omega I squareds down the middle. This term, what is this term? Well, it depends. Often, but not always, often, you're going to end up with this being a non-diagonal matrix. So the equations are still coupled together, okay? Your motion of Q1 will depend on Q2 and Q3 and so on, okay? There's a certain condition that C has to undertake for it to be a diagonal matrix, okay? And what that means is that we have, in general, the modal damping matrix will not be a diagonal matrix and the equations will not therefore uncouple. But there is a condition where they will uncouple, and that's where C is written in this form. Some coefficient times by the mass matrix plus some coefficient times by the K matrix, okay? And that's known as linearly proportional damping, okay? It's linearly proportional to the mass and the stiffness matrices, okay? A1 and A2 are just constants, okay? So if your damping can be written like that, okay, say damping is going to be basically proportional to the stiffness matrix. If A1 is 0, and your stiffness matrix is quite straightforward, and you can just apply a number to the stiffness matrix and you've got your damping matrix, then that's fine, that's linearly proportional. Okay? So that's what I said, damping is proportional to a linear combination of the mass and stiffness matrices. And like I said, that's known as proportional damping. And simplifies the analysis because the equations uncouple. Hunky-dory, you can go through the process. If your damping is relatively low, basically you just assume that it has the form, but it's not valid in all situations. And one particular situation that's relevant where it's not valid is with a car suspension system. Okay, your car suspension system is 2 degrees of freedom. So the mass of the body of the car, or in fact, I'll call this the sprung mass. Okay, you've got a spring and your shock absorber, and you've got your mass of your wheel, so that's the mass of the unsprung mass. And then obviously what you've got is you've got a spring, and there is some damping, and there's the ground. 2 degrees of freedom, we'll call this XU, or ZU in fact, because it's in the vertical direction. We'll call this ZS, because it's the sprung mass. And obviously here you've got the K of the spring and the damper that's involved in the sprung mass. And here we've got the K of the tyre and the damping in the tyre. Now normally with this problem, CS is much, much bigger than CT. Okay? And so what happens is your damping, C, is not going to be linearly proportional to your mass and stiffness matrices. This is much lower than this, and so you can't basically uncouple the equations. You can't apply this process to this problem because of this situation. Okay. Damping will not be linearly proportional. But, like I said, for other 2 degrees of freedom, especially ones where there's no damping, then you can therefore, theoretical modal analysis we can use, okay? Now, if it is the case where you've got proportional damping, then basically your diagonal matrix will be 2 zeta omega 1, okay, omega I, where zeta I will be your damping ratio, okay? And so your equation of motion ends up looking, your equation for Q ends up looking like this, okay? And again, we've solved that equation because again, on your equation sheet, we've got equations that give us solutions to mx double dot plus cx dot plus kx equals f of t. We've gone through and given you general solutions for that equation. So here, obviously, m equals 1, c is 2 zeta omega I, and k is omega I squared. Okay, so you make those substitutions in and you get your equations.